Everything works. Thank you.
All right, so we can start immediately. And this talk is about a very interesting topic, is about fake and deep fake content. And this is the outline. So we're gonna look at three different parts. The first one, we're gonna look at the problem. We're gonna look also at the opportunity that is opened by deepfakes. The second, we are gonna look at how to fix the bad part and keep the good part. And finally, we're gonna check out an interesting use case where I have personally worked in the last year or so. It's about liveness check in banking customer re-identification. So first of all, a quick introduction. What are deepfakes? Let's start with real content. So this is an example of a picture that probably a lot of people already know. So this is a real picture that was taken probably 100 years ago, but this is another picture. While you can probably imagine that the one on the right is real, the one on the left, it's not real. Now this is considered a fake image, so an image that doesn't correspond to reality. Maybe you can already see some cues that make you think that this was a poorly photoshopped image. Maybe the proportion of the face in comparison to hands and so on. But what if I show you this picture? So this is a completely different story, right? Because if I was asking you who is the real person and who is the fake person, I mean, personally, I would struggle, right? So obviously we can't raise our hands, but make your own guess. Okay, couple of seconds for making the guess, and this is the right one. So the picture on the left is a real picture with a real person. The picture on the right is what we call a deep fake. So this person or this baby does not exist. Okay, so it's an algorithm that created it, an algorithm that produced this image from scratch. Let's have a look at another example. So let's try to guess. Again, I'm going to give you 3 seconds. What is the answer here? Any guess? If you want, you can write on the chat. Well, this is the right answer. The one on the right. And the one on the left, I mean, this is pretty legit. I mean, when I saw it, I actually made a mistake, and so on. We can go on for hours. There's actually a website that challenges you on this interesting topic, and it essentially allows you to make these comparisons, and then guess which one are the fake and which one are the real. Now, obviously, the story doesn't stop here, yeah, right? So the story goes further, and it is also, related to videos. In this case here, you can see an example of a deepfake video where you see the right actor, Sean Connery, the amazing Sean Connery, who passed away actually a couple of weeks ago, and another actor, I think it's Burt Reynolds, where essentially one interprets the other. So again, in this case, you can see that is pretty damn realistic. So we can really look at the right version of the clip and believe that this is the real action. So in this case, it's a different technique. It's a different type of deep fake, because here what we're doing is we are taking images from another actor, Burt Reynolds, and we are pasting it, if you wish, into the original scene. Now, as you can imagine, this technology is very powerful indeed. And for every powerful technology, there are always at least 3 different sides: the good side, the bad side, and the ugly side. So let's have a look at each one of them one by one. So when it comes to the good side of deepfakes and GANs, as I write here, there are 3 interesting opportunities. The first one is certainly around storytelling. As you know, the studios in Hollywood and also in India, in Bollywood, for instance, they are creating visual content 24/7 and on a large scale. So a lot of that effort is manual. It involves real actors. So if you want to scale, and here I'm thinking, broadly, I'm thinking about Netflix, I'm thinking about, content creation at a web scale, you need some sort of automation. You need to be able to essentially take something that is real and tweak it until you get the desired outcome. Then we are, in this case, talking about assistant content creation. Finally, the third point is about enhanced communication. What if I was able to take images of myself and then animate my face on a different presentation, on a different talk, so that I could essentially morph this type of content that I'm delivering right now live into another content that maybe I've already written. So these are all examples of the good side of deepfakes and GANs. But let's have a look at the bad sides. Well, we have already experienced them, right? To some extent. Fake news, now they are ubiquitous. They are populating, sadly, social media and other specific parts of our life. Politics, there's a lot of bias and a lot of, not only fake news, but also fake videos involving real politicians saying things that I've never said in real life. And then there is fraud. In this specific one, this third part is going to be, there is going to be the focus of the second part of this presentation. So we're going to look a little bit more closely to this problem. And then there is the ugly. And the ugly is about pornography, is about bullying, is all about, all the very disturbing things that can happen when a powerful technology, is in the wrong hands. But let's focus on the right side of the story, or the good side of the story. So there are a number of companies that are already using deepfakes and generative machine learning, like for instance, Allure Systems. This is a French company, and this French company is essentially creating virtual models for fashion retailers. So essentially, the idea is very simple. You're a retailer, you want to create collaterals for a specific item, like for instance, a top, Nike top, and you want to, show to different people a different kind of assets, and you want to maybe even micro-target your audience. How do you do it? Well, you can essentially change the aspect of the model depending on who is in front of the camera and who is in front of the screen. So you can tweak the skin tone, you can tweak the look and feel, you can tweak many different parameters, actually an infinite number of parameters. Another example that I found fascinating, this is about dubbing, and the company is called Synthesia. We're talking here about automated facial reanimation. This is another interesting problem. You take an original video of your face and then you turn it into something different. You turn it into a new video that is animated with a branded new script. So again, guys, I know it's hard, but I hate monologues. So if you have questions, if you have comments, if you want to engage with me live, please write a comment or write a questions in the chat. Is here in front of me, and I will be able to hopefully address it and elaborate on that specific points, comment or critique live within the next few seconds. So let's move forward and let's conclude this first part, which is about the introduction to the problem. So now let's have a look at the, let's get into the meat of the discussion. So what is the technology and what is the breakthrough behind all these examples of deepfakes in videos, in images, and what are all these amazing research ideas about that are fueling all these new companies and all these new content creation and content revolution. So the technology, many of you already know it, maybe it's called the Generative Adversarial Network. Okay, so we're going to look at what is a GAN, how it works, and we are also going to look at some results. Now, first of all, it's all in the names, and in this case, it's again in the name. GAN is about a generative machine learning approach, and it is generative because through generative machine learning, we are able to create outputs that look like the ones that we have in our original dataset. And this is a very crucial and important point. This is what essentially differentiates generative machine learning from other types of machine learning, like for instance, supervised or unsupervised machine learning. Now, when it comes to the adversarial part, the idea here is that we actually train two different models in a zero-sum game. I will explain later what it means. But the intuition here, it's very simple. There is one model that has to fool the other. Let's look at the last part, which is the network part. So here, as in many other machine learning or deep learning models, we are dealing with a neural network architecture. Okay. So if you were asking what is a GAN to Russell Crowe, or better, John Nash, who is the father of game theory, John Nash will say that a GAN is a zero-sum game. Now, before I explain what a zero-sum game is, let me address a question from Rahul. Rahul is asking me, what are your views on IP infringement, and how can we tackle this issue? Well, yeah, first of all, Rahul, thanks a lot for this question. This is a fascinating question. There is already an awful lot of work that has been done in copyright infringement. I'm aware of several companies, actually, like for instance, TinEyes, who are looking at the specific problem of copyright infringement in video and images. So for images, this solution is already there. It's called the reverse image search. So essentially, given an image, I will give you an example. So let's say we take this image. We take the image of Russell Crowe in the ads of the advertisement picture of Beautiful Mind, amazing movie about the life of John Nash. So we would then take this image and crawl the internet for similar images or images that look like this, but maybe they have some variants. Like for instance, there's a crop. For instance, the infringer has changed the color or has changed the fonts. So in this case, deep neural networks can help because they can recognize or match on a very large scale the original versus fake. Any other questions, guys? Anything else you would like to discuss about this copyright infringement? I think it's a hot topic. It will be a hot topic even in the future. You know, YouTube and other platforms have already, this technology deployed, but many others need it. All right. So if there are no other questions, I would like to move to the next part, which is about zero-sum games. So here, a zero-sum game is actually very simple. It's a game where when I win, you lose. Or if we are using a more up-to-date and relevant example, Brexit scenario one, hard Brexit, either one win and the other loses, or a non-zero-sum game interpretation of this is a soft Brexit, where there is an overlapping set of interest and where we both win. With GANs and with deep learning in general, the interesting thing is that we have this two players game. One is a forger, that tries to make fake money, and the other one is the police that is trying to allow legitimate money, and it is also trying to catch counterfeit money, right? So let's call the forger a generator. So the generator must learn to make money, and such money should be indistinguishable from genuine money. And then there is the police that we call the discriminator, that is trying to create samples drawn from the same distribution of the training data. Fairly simple. So again, it's a two players game, one against the other. How does it work? Well, we said that we have real money, police has access to real money, and the forger has also access to real money. So what happens here? Well, the forger tries to imitate badly, in this case, the $10 note, because just started, and the police has no problem. It is able to understand, as you can see here, that this note is fake. But what happens as the training progresses? As the training progresses, the generator gets closer and closer to producing outputs that can fool the discriminator. So in this case, it's still quite simple to understand that it's fake, but then what happens when I get to an output, or when the discriminator is, is getting a note like this one? Well, it's going to be much more challenging to understand this is fake or real. So this is exactly how a GAN works. So this is exactly how a GAN is trained. So we have this forger, this generator, that creates a sample. The sample is evaluated by the discriminator, or the police, that also has access to the real images. And then the discriminator will have to be able to assess the work that has done, and we will measure the errors that the police makes in terms of discrimination loss. This is a technical term that essentially captures the amount of information that the discriminator learned. Obviously, also the generator needs to be trained, and the performance need to be learned, and this is achieved through the generator loss. It is worth noticing that the generator is initialized, or let's say initialized or fed with a random input. So we initialize the generator with random numbers, and then iteratively this forger enables or learns how to translate random numbers into real notes. This is the most amazing part, I think. Let's recap, guys. And before I do this, I'm going to drink my tea, and I'm going to ask you again, do you have questions? Do you have comments? Do you have things that you think are unclear? I see that Reynaldo is saying, nice example. Thank you, Reynaldo. I'm happy about this. Actually, this example comes from developers Google. So this is very important. Attribution is very important. So if you want to know more about all this stuff, there is an awful lot of material, especially on the Google TensorFlow page. So don't hesitate about going there and check out more. All right. So if there is no more questions, no more open points here, let's move on. I actually forgot to drink my tea. So here, I just wanted to give you an idea of how this workflow looks like. So we have, as I mentioned, a random sample of data points. We feed the data points into the generator, and in the forward pass, we want to transform this random variable into plausible, let's say, plausible data. As you can see, this plausible data is kind of overlaying on the real data, which is the blue distribution. Still not great, but better than the input, which was completely random. Amazing. So this is in the forward pass. What happens in the backward pass? Well, essentially what we do here is we are taking the error, and we back propagate the error to the network. So let's recap. We forward pass, we backward pass the error, and we tune the machine, we tune the generator. This is, machine learning 101 for you guys who have already trained deep learning networks. This is not new. I put this here because not only you have to do this for the generator, but you also have to do this for the discriminator. And the reason why I am sharing this with you is that when you're thinking about a GAN, here the training and the loss are a little bit trickier because you have essentially these two networks to train simultaneously. And in an adversarial zero-sum game, there is a generator, which is the forger, and there is the discriminator, which is the police. Now, if you want to forget everything about what I said, please don't forget this part because it's really relevant. So let's say that both of them, the forger and the police, have to be evaluated on an error, and the error is the classification error between the correct and the incorrect answers on the authenticity of the node. Okay, so we have this error, and we have these two entities that we need to evaluate. So how do we do it? Well, in one case, the police has to minimize the error. So the police wants to be always right, while the forger wants the police to be always wrong. Does it make sense? I think so, right? So what you want to remember is that the forger or the generator wants to maximize the classification error at the end of the GAN, and the police or the discriminator wants to minimize such error. Okay, so I found this particularly helpful and particularly useful. It's a very simple, concept, but it gets trickier and it gets buried under the way when you are looking at at all the details. So please remember this. I just would like to give you a final intuition on the difference between the usual models, discriminative models, where you have an input data, you have a model that is pre-trained, and it gives you a predictive classification. And then another model, which is the generative model, and where essentially you are creating data samples from scratch. Now, before I give you some results on the evolution of GANs, there is a question from Max. Now, let me first read the question. Do the discriminator and the generator use the same data as training? For instance, do they draw from randomly from the same data pool? Okay, this is a very, very good question. So let me try to go back and address, and then Charles, I'll try to address your question. So when we are talking about the generator, the input of the generator is always a random distribution. When we are talking about the discriminator, we are taking a training set with a random sample or a stratified sample of images. Then second question, Charles, why not showing the math behind GANs? That would be much more understandable. Yeah, good remark. I'm always trying to simplify things, and maybe this time I oversimplified. I prefer, to bore, part of you guys who are, expert in this field than, lose all the others that are not very familiar. But, I'm very happy to jump into a call or share more technical details about the math that is behind all this. Okay, so let's move forward. Time is flying. I think we have another 10 minutes. So let's try to, keep it, relatively short and punchy. Any more questions? Maybe there is room for another question. Okay, so if there are no other...
I just wanted to say we still have 20 minutes, so no need to rush.
Okay, Micah, thank you very much. I'm not going to rush. But I still would like to leave 3 or 4 minutes at the end for open-ended Q&A. I just here would like to give you an idea of how fast and how dramatically the quality of the outputs of these GANs evolved over time. So here it's an example of a generated face in 2014. This is 2015. You can appreciate that the second image is in color. There are probably less artifacts, actually not. I see the JPEG artifacts around the eyes and in the mouth, but yeah, there is certainly more details. And you know, the face is tilted, so there is a slight little pose that makes this a little bit more real. And what happens in 2016? Much more detail. Hair, better pose, still not very realistic. But look at 2017. This is real stuff. So the evolution, this evolution is, I think, due to three different breakthroughs. First of all, yes, there is the fact that in 2014 GANs were still at a very early stage, but then there's also, you know, an awful lot of tweaking that went on in the GAN. Now you can really have a lot of different varieties, different architectures that are optimized for faces, and then there is, you know, the big data. So we have much richer data sets, and I'm going to share one of with you guys if you want to experiment with them. So we are transitioning now in this second part of this presentation, where I'm going to now talk about a specific problem I work with in the recent past. It's about liveness check. So it's a very specific problem that potentially can be created by GANs and by fake video content. Okay. So before I do this, again, if you have questions or comments about the first part, about the results, just fire a note in the live chat. It's in front of me. I can address your question. Okay, so when we're looking at this problem, it's really like a dog biting his tail, right? So for each new discovery in forgery detection, there is a new GAN architecture breakthrough that makes the detection even harder. Now, it's not a surprise that, you know, the big guys are all looking at this problem and they are struggling. So this is a daunting task, and even Facebook and Microsoft are actually struggling. So what do you do when you don't know how to solve a problem? Well, very simple. You create a Kaggle challenge, and you hope that someone else smarter than you will solve the problem. So this is exactly what they did last year. So this is actually, it was early this year. They launched it early this year in June in CVPR. They created this deepfake detection challenge dataset. And the interesting thing is that they have a full dataset of 125,000 videos. And the idea is that, you know, you take the challenge and you try to understand what are the fake videos and what are the real videos. So this is a very, very fascinating topic, largely unsolved. And again, your Facebook, your Microsoft, what do you do when you want to solve a machine learning problem? You just throw more data at it. And this is essentially the evolution of the data sets over time. This is the deepfake data set that I showed you before. It's yeah, it's really big, but is this a quantity, or let's say it's this? What is the challenge here? This is certainly not a problem where the more data you throw at it, the better you are, because as you can see from the best results, 82% accuracy, we're still very far away from you know, a usable model, a usable set of techniques. So what I'm saying here is that while 82% is already a very good baseline, if you want to roll or deploy this technology into production, there's still a very long way to go. I have a lot of clients that come to me and say, hey, well, it's working, it's 85%. And then I tell them, look, getting to 85%, you know, a guy from university, smart guy in the university can do that, but from 85% to 95%, which is the jump that you need to bring that technology into production, that's a very big deal. And that's the reason why they actually come to us. So the idea here is that you develop a set of techniques that are essentially trying to predict whether or not the content that you have in front of you is real or fake. Now, you can't use a GAN as it is structured normally as a generative network, but you can use two sets of techniques. First of all, you use heuristics. So for instance, these GANs are not perfect. So for instance, in this case, you can clearly see that there is something going on with the hair. And even, as a human, our brain is trained to detect the smallest alterations on your face. So in this case, the hair looks weird. It looks like it's painted. In other situations, you have artifacts. So the text is unreadable on the background. And by the way, we know that GANs are struggling with text generation. Or here we have surreal backgrounds, some weird abstractions going on. Last but not least, there is another example. Here we have problems with asymmetries. So already we have a situation where we are able as humans to distinguish some cases, the easy ones. But what about the most challenging and complex situations where we have an image like this, which is real, and the equivalent fake, which is very similar to the original? So in this case, we can use signal processing techniques that are able to separate the fake from the original. Now we can be much more complicated than that. And this is an example where I will show you in this third part something that we did, where instead of using signal processing, instead of using heuristics, we were using another deep neural network for checking liveness of a person. So here we are in a personal banking use case where you want to re-identify a user of a bank. So you have an app, you have a bank, you have an app, you have somebody in front of you, and you want to re-identify this person. Re-identification is a very different problem from the usual problem of face recognition, because in this case, it is actually what's happening in front of your mobile phone, in front of your iPhone. So what you do here is you take the photo of a person and you compare the photo of the person with the one that you already know. And you have to give an answer, a binary answer on whether or not this person is matching. Any questions or comments? Everything is clear. I mean, this is very simple stuff. The less simple stuff when it comes to the banking scenario, as you probably can already imagine, is that people are, I mean, not people, but cheaters and thieves essentially are trying to do is to use different techniques to attack and also to break the system. Before I go into the details of this, I will address a question from Fernando. Can we use some kind of GAN for synthetic text generation? Absolutely. There are a plethora of different models. Thank you, Fernando, for your question. So there's actually an awful lot of new models in the natural language processing field. A couple of months ago, there has been yet another one called the GP3, which is a brand new model that is able to automatically generate text that is super accurate and in some context very, very ready for deployment in real case scenarios. So Fernando, please, if you want to check out text generation, just Google GP3 and you will see a world opening in front of your eyes. So thank you for the question. Any other questions before we move on and we look at this final example? Is GP3 considered as a GAN model? I would consider it as a generative model, but I don't know if we could define it as an adversarial model. We need to double check it. Thank you. Any more questions? Okay, so let's move on. So we saw that there was this problem. So people put in front of the camera a picture, a high resolution picture, a paper, a picture, and this can fool the app face identification. A second problem is, people are putting in front of the camera another mobile phone with a high resolution digital photo or even a video. Okay, so this is this is getting harder because there are other malicious users that can even wear a mask. So how do we prevent all this without introducing a lot of friction into our customer journey or user workflow? So obviously it's a trade-off, and the trade-off is between the user experience and the level of security that we want to achieve. When we're talking about a banking application, obviously we have to go off the chart on the x-axis. So we want a super secure architecture and solution, but we still want a very good experience. So we really want to be positioned there. So how do we achieve this? I'm not going to go into details of the requirements because I don't think it's the scope here. So I'm going to give you, unless you guys want to get into the details. So please, ping me in the chat if you want all the details. Otherwise, I'm going to give you the gist of the story with an example. So you have a mobile phone in front of you. You have a user that is looking at the phone, wants to log in. How do I understand if this user is alive, is in front of the camera or not? Well, I can ask the user to collaborate with the app, and I can ask the user to look at a specific region within the screen of the phone. So what I could do is I could then change the position of his gaze by changing the rectangle position. Okay, so here what you can see in this very simple animation is a rectangle that changes position, right? We will see in the demo how this works in practice, but I think it's pretty clear, right? So the first question is the same person in front of the camera? Yes. Now, is this person alive? Is this person real or fake? And this is the second follow-up question. So how do we do it? First of all, we have developed an app. For the moment, it's an Android app, and the Android app just takes the camera, samples some frames, actually samples, I think at 5 or 10 frames per second, not too much. I think 10 frames per second is enough. And then after we acquire the data, we are detecting face. We are then looking at the quality of the face, and we are detecting the eyes as well and the mouth. And then we are tracking the gaze. Once we are tracking the gaze, we are classifying the gaze position, and we are able to predict whether or not the person is alive or fake. So let me give you an example, and then we're going to look at a video that I recorded this morning and wrap up the presentation. So here we take an input frame, then we detect the face, the eyes, and we mask these different regions. And by the way, this is a model trained by some folks at MIT. There is the reference of the paper here if you're interested. We implemented it, and here to implement it actually is it's fairly straightforward. You have to train 3 different convolutional neural nets, one for the eyes, one for the right, one for the left eye, and one for the face. And then you also train a different network for the face grid. Finally, you combine all the outputs using max pooling, and then you predict your gaze. Any questions or comments about this, guys? I'm going pretty fast because we're closing up. But again, my email is on the chat. If you want to interact with me afterwards, just send me an email and we can organize a quick chat. So no questions, no comments. I know you're tired, guys. Lunch is coming, so we're gonna be closing up in 4 minutes. So let me show you this video. So this video essentially shows you myself in front of my my Samsung, and here you see a lot of things going on. So the first thing that I would like you to focus on is my face and the rectangle around my face. So this is pretty straightforward. Even 20 years ago when I started my PhD, we could do this. We can do face detection with our filters. We can do face detection now even with DLEEP and with more complicated deep learning based solutions, but this is not the interesting bit. The interesting bit is that we are predicting we are detecting the eyes, and from the images or the sub-images of the eyes, we are able to predict where the gaze is. And the gaze is represented here in the orange ball, okay? So I'm moving the eyes, and this orange ball is moving into this screen. Now, you could ask, what's the story with the blue or navy ball? So the navy ball is the ball that I am following with my eyes. So navy ball is the ball that is essentially, it's like a password, right? It's like a password that is randomly generated by the system. So I'm looking at the blue ball, the machine learning is looking at my eyes, predicts the position of the eyes, paints the orange dot, and hopefully the orange dot is matching the blue dot. Is it perfect? Not at all. It has an error that is appropriate for this kind of application? Maybe. Certainly for iPads and tablet devices. Now, there is a question from Anja. Does it also work if a person has one eye? Yeah, that's a great question. I never thought about it. Yes, I mean, if you have only one eye, the detection would be a little bit less robust, but it could work because let's not forget, guys, here we are feeding our convolutional neural network with a lot of information, the right eye, the left eye, the face. So even tiny movements of the face or the formations of the muscles of the face can have an impact and can be useful for classifying and predicting the position of the gaze. So I hope you got the benefit of this solution. It's super secure because we are able to, we are not able to fake this, right? So we're not able in real time to have a generative model that creates a face, that moves the eyes in the right way, or at least not yet. Okay, maybe in 3, 5, or 10 years time. But the second interesting thing is that it is adaptive. It can be rolled out into a mobile device, and this is what I'm showcasing here. And then the third thing is that it is relatively lightweight. There is another question from Gunther. There are real-time deepfake system yet which just applies my face to another? Yes, there are deepfake systems that do that. And again, in the literature, I have listed such systems. All right, guys, if you want to have a look at, I'm going to skip this because we're out of time, the conclusions. So number one, GANs are not a bad technology. Number two, there is incredible potential. And I want you to remember this, incredible potential and a lot of room for improvement on this great technology. And then the fight is not over. As I was mentioning before, there is an awful lot of work going on in both sides, from the forgers and the police.